we have been discussing with the effectiveness-NTU method for the design of heat exchangers, and I have told you in the previous class that this method is useful when we do not know any of the outlet temperatures. So the inlet temperature of the hot fluid and the inlet temperature of the cold fluid are known, but we do not know the outlet temperatures. So use of LMTD approach for calculation or for design of such systems becomes tedious, as we have to go for an iterative solution. So the effectiveness method takes care of these unknown values of the outlet temperature and expresses the effectiveness, which was denoted by epsilon, in terms of NTU, where NTU is defined as the number of transfer units. So in the last class we have defined what effectiveness is and how effectiveness and NTU are connected for a simple situation of a parallel flow 1-1 heat exchanger. But we did not complete it in that class, so I will continue with the derivation of the pertinent relation between epsilon, NTU and so on for the case of a parallel flow heat exchanger, and we would see what would happen if it's a counterflow, if it's a system which contains multiple tube passes and possibly multiple shell passes as well, and what's going to happen if it's a boiler or a condenser, such that in one of the streams the temperature will not change. What would be the value of epsilon, or what expression would result between epsilon and NTU when one of the liquids, one of the fluids is undergoing phase change, as in boilers or condensers. And then towards the end we would see that all these results for the epsilon NTU relation, the relation between effectiveness and number of transfer units are provided in the text in the form of tables and graphs. So in the next class we would solve a problem to see how to calculate the epsilon, the NTU, the unknown temperatures and so on through the application of an example. But today again, as I start with the basic definition of the effectiveness and how it is going to be connected with NTU and so on. So I'll quickly go through the slides which we have discussed in the last class, and then move on to derive the final relation. So what we have done in the previous class is we started to work on epsilon NTU method, and the maximum amount of heat transfer, the maximum possible heat transfer can take place when the temperature drop goes from THI, that is the temperature of the hot fluid, to TCI, temperature of the cold fluid. So that's the maximum possible temperature difference that exists in a heat exchanger, and if the temperature of the hot fluid reduces to the temperature of the inlet temperature of the cold fluid, or the temperature of so this is going to give rise to the maximum possible amount of heat transfer. However, if the capacity, where the capacity is defined as m dot Cp, so Ch, capacity of the hot fluid, would be m dot Cp corresponding to the hot fluid, and for the cold fluid it's simply going to be m dot C times Cpc. So if Cc is less than Ch, then the maximum amount of heat that can get transferred would be Thi minus Tci with the Cc. And similarly, the simple logic would tell me that whichever is the lower of the capacity between the cold and the hot, the Qmax is simply going to be the capacity of that one which is the minimum. So I can write Qmax as equal to C minimum times Thi minus Tci. So this is the maximum temperature drop that can take place. So Qmax is simply going to be related by this. The effectiveness was defined as the actual heat which has been transferred divided by the maximum possible heat transfer, and the maximum possible heat transfer corresponds to a length of infinite length of the exchanger. So the actual heat transferred can either be Ch times the temperature difference between the hot fluid inlet and the outlet, or Cc and the temperature difference between the outlet and inlet for the cold fluid. So these two are the numerators are the actual heat that has been transferred, and obviously through heat balance these two are equal. Whereas the denominator is going to be, as I said, C minimum times the maximum possible temperature drop that is possible in a heat exchanger. So it's C minimum Thi minus Tci. And as you can see from the definition, the epsilon will lie between a value of 0 and 1. And if we know the value of epsilon, the value of Thi and the value of Tci, then the actual heat transfer is simply going to be Q equals epsilon. So if you simply look at this expression, it's going to be epsilon C minimum Thi minus Tci. That's the total amount of heat transfer. Since Epsilon-NTU method is used when the inlet temperatures are known, so therefore Thi and Tci are known to me, and therefore it is possible to calculate the heat transfer, the actual heat transfer, based on the difference of the inlet temperatures, provided epsilon is known. So the entire exercise that we are going to undertake in this part of the course is to find a relation between epsilon, and for any heat exchanger epsilon is going to be a function of NTU, where NTU is defined as the number of transfer units. It's UA by C minimum and the ratio of C minimum by C max, which is sometimes also referred to as CR. The ratio is expressed as CR. So then we went into this effectiveness-NTU relation, and we started to derive the expression for a parallel flow, as I mentioned before, parallel flow heat exchanger with C minimum equals CH. So CH, which is m dot Cp, both for the hot fluid, is the lower one. So therefore epsilon would be the total actual heat transferred divided by the maximum heat transfer that could take place, and in this case C minimum is simply going to be equal to CH. So CH and CH would cancel from the numerator and the denominator. So your epsilon should simply be the temperature change of the hot fluid divided by the maximum change that can take place in a heat exchanger of infinite length. So it's Thi minus Tci. The C minimum, capacity C minimum by C maximum, is simply this. In this specific case, H is the minimum and cold fluid is the maximum, and for a parallel flow this is how the temperature would change. So the hot fluid would decrease from Thi to Tho, whereas the cold fluid temperature would increase from Tci to Tco, and the delta T1, which is the temperature difference existing at the inlet, is simply Thi minus Tci, and the temperature difference between at the outlet is this difference, whereas in between it's going to vary in a non-linear fashion. And we already have seen that the pertinent delta T to be used for such cases is the log mean temperature difference. So the overall temperature difference, the average temperature difference between the inlet and the outlet, is simply the log mean temperature difference. And since it's a 1-1 heat exchanger, so it's a parallel flow simple 1-1 heat exchanger, so no correction factor to LMTD needs to be provided. So whatever be the LMTD that we calculate based on the inlet temperature difference and the outlet temperature difference can simply be used to express the total heat transfer in the form of Q equals to UA delta T LM, where U is the overall heat transfer coefficient. The overall heat transfer coefficient consists of the convective resistance at the inside of the tube, the convective resistance at the outside of the tube, and the conductive resistance of the pipe wall if the pipe is not thin. So if the pipe is thin, the overall heat transfer coefficient has two components. One is HI, the heat transfer coefficient based on the inside of the inside area inside of the tube and HO. To this, sometimes we add the dirt factor, which is simply the deposition and scaling of the inside as well as the outside of the tube that can lead to significant resistances. So all these resistances are going to be in series. So 1 by twice by HI times HI twice by RI is the resistance based on the inside convection in a pipe. Then RD is the dirt factor, and 1 by twice by H naught times R naught is the resistance at the basis of the outside of the tube area. So U is defined. Therefore, Q is equal to U times A times LMTD, and with no correction factor for this specific case. This Q is also equal to the CH, the capacity on the heat side, capacity of the hot fluid, temperature drop of the hot fluid, capacity of the cold fluid, and temperature drop of the cold fluid. And this is simply the definition of LMTD, which we have seen before. So therefore, from these two relations, I can write the temperature difference of the hot side is simply Q by CH, temperature difference of the cold side is simply Q by CC, and since Q is equal to this, so Q can then be equated to UA by ln delta T2 by delta T1, which is outside over here, and THO minus THI minus THO and TCO minus TCI can be expressed in the form of Q by CH, as I have shown before. And therefore, upon simplification, what you get is simply this factor, and therefore the temperature jump at the temperature change at the hot inlet temperature, hot outlet temperature and cold outlet temperature divided by the maximum temperature drop that can take place is going to be exponential minus NTU 1 plus C min by C max. But this expression still contains the outlet temperatures. We cannot deal with outlet temperatures since they are unknown to us, and the whole point of doing the NTU epsilon analysis is to get rid of the outlet temperatures in the final expression, such that we can use that. So we start from this point. I'll write the expression once again over here: THO minus TCO by THI minus TCI, which is the maximum temperature drop that is possible, that is attainable in a heat exchanger, which would require an infinite length, exponential minus NTU 1 plus C minimum by C maximum. So this is the expression which we are going to start with, and which we would like to solve. So starting from this point, that's the starting point of the exercise in today's class. So we will start with this and try to get rid of the outlet temperatures. In order to do that, I express THO minus TCO by THI minus TCI as THO minus THI plus THI minus TCO. I have simply added a THI plus and minus in the expression. The denominator remains the same. And from our previous expression, if you look at our previous expression, which we have done at the beginning, which is C minimum by C maximum. Let me see if I can figure this out. This C minimum by C maximum, we have obtained it as TCO minus TCI by THI minus THO. So I can start using this expression, C minimum by C maximum is equal to TCO minus TCI by THI minus THO. So that's the expression which we have obtained. This is simply a heat balance. So from here, TCO would be equal C minimum by C maximum times THI minus THO plus TCI. So this is simply from heat balance. Okay. So the TCO, as I said, the idea is to replace THO and TCO from the expression of this. So the first expression for TCO which I have obtained is from a heat balance. So therefore my THO by TCO by THI minus TCI is equal to this, THO minus THI plus THI, and then instead of TCO I bring in this expression, so it's going to be minus TCI. So when I put this expression of TCO in here, then what I get is THI minus TCI minus C min from this expression, C min by C max, the temperature difference of the hot side of the fluid, and the denominator remains unchanged, which is THI minus TCI. So now if you look at the expression THO minus THI by THI minus TCI, this is nothing but minus epsilon, because the definition of epsilon which we have used so far, which we have used here, this is the definition of epsilon, and since CH is the C minimum in this case, so my epsilon is simply THI minus THO by THI minus TCI. So over here THO minus THI by this is nothing but minus epsilon. This will simply be 1, and what I have over here, what I have over here is simply C minimum by C maximum, and THI minus THO by this is simply the definition of epsilon. So this is the expression which I get when I replace the expression in this form. So everything is in the form of epsilon. So I simply reorganize it a little bit. So taking the epsilon common, it's simply going to be 1 minus epsilon 1 plus C minimum by C maximum. So this is just the ratio what you would get. Also we know that THO minus TCO divided by THI minus TCI is exponential minus NTU 1 plus C minimum by C maximum. This we have derived before. So this obviously would be equal to 1 minus epsilon from the previous one, 1 plus C minimum by C maximum. So what you would see here is that this temperature difference containing two outlet temperatures is now replaced by an expression containing epsilon and NTU, but it does not contain any of the outlet temperatures. So this is the beauty of the Epsilon-NTU method, starting with a simple definition of epsilon, and for applying it for the case of a parallel flow heat exchanger, 1-1 heat exchanger, in which C minimum is taken to be equal to CH, and by making simple suggestions, statements, heat balance, definition of epsilon, definition of NTU, we have arrived at an expression that contains only epsilon and NTU. And what is NTU? NTU contains the overall heat transfer coefficient U. So the overall heat transfer coefficient of the heat exchanger can be obtained if through the relation between epsilon and NTU. So this expression that we have obtained for epsilon NTU for parallel flow heat exchanger, 1-1 heat exchanger, in which CH is the minimum, CH is the minimum capacity, that means CH is less than CC, can also be obtained when in a similar fashion when CC is the minimum, that is CC is less than CH. So this is the simplest possible form of epsilon NTU relation, and I will just simply complete this to give you an idea of what is the final form of epsilon going to be. So epsilon from here would be equal to 1 minus exponential minus NTU 1 plus C minimum by C maximum So this relation one can derive for the case of parallel flow 1-1 and C minimum is equal to CH. Same result can also be obtained for the case when C minimum is CC. So the above equation applies to this equation applies to any parallel flow heat exchanger. That's what is important. Similar expressions have been developed for a variety of heat exchangers, and I will show you some of the expressions over here. For two or more shell passes, when I have two or more shell pass, NTU is to be replaced by NTU by N. Now, for a boiler or condenser, let's say the temperature of one of the phases will remain constant. So if it's a case of steam condensing on the outside, then the temperature of the hot stream is not going to change. It will remain constant at that value. On the other hand, if you have evaporation taking place, then the temperature of that phase will also remain constant. So there's not going to be any temperature change for the case of boilers and condensers. So let's see what expression epsilon would take for the case of boilers and condensers. So for boilers and condensers, so only phase change is taking place. No temperature variation. So what is going to happen is this CR, which is the ratio of C minimum by C max, this would be equal to 0. and the important thing is the heat exchange behavior is independent of flow arrangement. So it does not matter if it's in parallel flow or in counter flow, because that concept does not apply when the temperature of one of the phase is remaining constant. So essentially what it gives is the heat exchange behavior is independent of the flow arrangement, and from the previous one you can clearly see that this would lead to, where this is 0, this would lead to 1 minus exponential of minus NTU. Okay. So this is the expression for between epsilon and NTU when you have heat either a boiler or a condenser, and the heat exchanger behavior is independent of the flow arrangement. Sometimes for design it is more convenient to have not epsilon as a function of NTU, but NTU as a function of epsilon and C minimum by C max. And for this has been solved for a number of flow geometries, for a number of situations, and there are graphs available which would give you the value, the relation between NTU and epsilon for different values of C minimum by C maximum. So I will show you some of the graphs, and if NTU is less than or equal to 0.25, all heat exchangers have the same effectiveness. The same effectiveness, and regardless of what is the value of CR. Okay. And it is also shown that for CR greater than 0, NTU greater than 0.25, counter flow is definitely more effective than compared to parallel flow. So these are some of the observations which you can make when you look at the heat exchange, this curve. So what I show you here is from the text there are certain relations and correlations which can be seen for the case of parallel flow, for the case of counter flow, shell and tube with one shell pass, and multiples of 2 in terms of tube passes, n shell passes, and if you have 2 shell passes then there must be 4 tube passes and so on. In cross flow, then all exchangers for which CR is equal to 0, which is the case for condensers and for boilers, the relation between epsilon and NTU are provided in the text. So they have already been solved. I have only showed you the simplest example of parallel flow heat exchanger, but here in the text, in your text, in the book of Incropera and DeWitt, the textbook, you would see these kind of relations for epsilon and NTU, which are available for most of the cases that you can think of. As I mentioned, sometimes it's for the design purposes, it's better to have NTU in terms of epsilon. So the next table in your text gives you the same thing, but right over here the NTU is on the left hand side. They are related, the explicit relation of NTU with epsilon which are provided. for parallel flow, counter flow, shell and tube, and for all types of exchangers where CR is equal to 0. So these are the relations where NTU is expressed in terms of epsilon. And the figures that I was talking about, it's also from your text, where you do see is the effectiveness epsilon of a parallel flow heat exchanger, which is the equation number 11.28 in the previous page. And you would see that the values, what you can do is you can find out if you know the value of NTU, and then you find out what is the C minimum by C maximum, read that, go to up to that point and find out what is epsilon or effectiveness of the heat exchanger. Once we solve a problem in the next class, it would be even more clear to you. So this is for a parallel flow heat exchanger, this is for a counter flow heat exchanger, where the effectiveness is expressed against number of transfer units for different values of CR, which is C minimum by C maximum. 0 corresponds to the case of condensers and boilers, and so on. And the last one that you see is when CR is equal to 1, that means C max is equal to C minimum, and this is the, so therefore let's say when water flows in both the shell and tube with the same flow rate, so m dot CPC is equal to m dot CPH, and this is the relation which you would get. And all these ones this is for shell and tube heat exchanger with one shell and any multiple of 2 tube passes, that is 2, 4, 6, etc. Again, this is the value for CR equals 0, and this is the value for CR equals 1. The values of epsilon are plotted against NTU, and you also have the shell and tube heat exchanger with 2 shell passes and any multiple of 4 tube passes. So that's the relation which has been provided. So this is for cross flow heat exchanger, which one can see, but we are going to restrict ourselves to these 4 curves, and when we solve the problem, we would see how the knowledge of epsilon can tell us what is NTU, or if I know the NTU for a specific process, can we calculate epsilon. And from the fundamental definition of epsilon, the moment I know what epsilon is, then I should be able to find out what is the inlet temperature and what are the unknown outlet temperatures of the hot and the cold fluid. So there are 2 approaches, as I mentioned, for the design of heat exchangers. If you know if you can find out from heat balance all the temperatures of the inlet and the outlet streams, probably use of LMTD is better suited for that condition. But if you do not know the outlet temperatures, an iteration is required to solve, to adopt the LMTD in such a case, it's easier to use the epsilon approach, Epsilon-NTU approach, where the significant number of graphical solutions or graphs available for different flow situations and different heat exchangers would enable you to do the calculation in a much more faster and direct way as compared to the iterative process of LMTD for that specific cases. So both approaches can be adopted. You decide based on the data that you have which one is going to be more suitable for faster calculation and easier evaluation of all the temperatures, and once you have all the temperatures, then you would be able to find out other design parameters. So we will talk a bit more about this Epsilon-NTU method in subsequent classes, but I think we have had enough information to solve a problem and clarify about Epsilon-NTU method and clarify some of the doubts and to enable you how to use these graphs, charts, relations and arrive at a solution. So the next class is going to be a tutorial on Epsilon-NTU method.